Hello, this is Keith Graham from Codasip. I'd like to introduce you to Assignment 8, Load and Store Instructions. In computer engineering, there is a type of architecture called a load-store architecture, which is an instruction set where you have two sets of operations. One set of instructions takes data from the register file, stores it into memory, and then takes data from memory and stores it back into the register file. And then the second set of operations are your ALU operations that only operate on data that resides in the register file. The RISCV architecture is based upon this load store concept. In this assignment, you will be implementing store operations, which will take data from the register file, move it into memory, and then load operations, which will take data from memory and put it back into your register file. In this assignment, you will be introduced into a new type of hazards, a structural hazard. A structural hazard occurs when a resource is not available for a pipeline to complete its desired operation in a particular stage. Now, if I have a store operation, the memory bus is going to be pointing towards memory and not towards the CPU. Now, if I turn the bus immediately around and wanting a load, I have a structural hazard because my memory bus is not available for one clock cycle after a store operation. This is an example of a structural hazard, which you will have to overcome in this assignment. You'll be overcoming this type of structural hazard by inserting a stall in the pipeline. So you insert a stall very similar to the way you did a memory no-op bubble in a preceding assignment by specifying each pipeline stage that you want to stall by pipe.stagename.stall. A stall will keep the output of the register file or the pipeline register independent of what the input is. The output will remain the same. We're stalling the pipeline register. Another type of structural hazard is the load data hazard. In this situation, the load result is not available until the very end of the memory stage, or in reality, the write back stage, where in the ALU, the data is available at the end of the execute stage, which makes it available for data forwarding in the memory stage. So load data is available for one clock stage later than the ALU data. That means the operation right after the load, if it requires the result of the load, needs to stall for one clock cycle. There's two ways of solving this problem. One is via software, where you tell the compiler not to insert an instruction immediately after the load that requires the result of the load. Find another useful instruction to place in that slot. The drawback of this operation is if I took binary code that was compiled on a different computer for RISC-V, which did not insert a different type of instruction immediately after the load, it might not work on my machine because of this particular hazard. So another way of solving this problem is to add a stall in the iFetch to decode pipeline register and the decode execute pipeline stage. If you insert this stall, the binary will work for your compiled code or any other binary code. The stall way of solving this hazard will be an extra credit option for this assignment, where the basic assignment will be using the software. Good luck on your project, and if you like this video, please subscribe to this channel so that you'll be notified when additional videos are published.